Okay, welcome. This is a video for Calculus 1 on our section 4.3, how the derivatives affect the shape of a graph. So this is what we've been working towards when we've been studying these critical values, the relative maximin or local maximin, all of that relative extrema work. This is all that Rolle's theorem and mean value theorem in order to guarantee us certain existence of some maybe horizontal tangent lines or other tangent lines, as well as our leading us to graphing without needing the graphing calculator. So that's sort of where we're going. So we're going to look at today a first derivative test as well as a second derivative test, but I will do it in two different videos so you can kind of break it up. So first, let's talk about this first derivative test. And I'm going to fill some of these in as we go. So again, you can follow along on paper or just watch for enjoyment or take your own notes or fill in these notes if you have them. So this first derivative test right here is if f prime of x is greater than 0, which for us means f prime of x is positive, for all x in the open interval AB, so that is somewhat important to note that open interval, then we say f is increasing on the open interval A to B. And it's important to note why it's an open interval A to B, and that's because we're talking about one moment in time. So if we see a curve that looks something like so, doesn't matter what it's doing to the left, I'm going to stop it. And I look at this one point right here that I just put in red. If I draw the tangent line at that one point, maybe it looks something like so. And if I look at the slope of that tangent line, that slope is some positive value. And that's because I'm allowed to now say my function at that point is increasing. Or from left to right, how we would read our graph, I can say f of x is increasing. We can also say the slope of the tangent line is positive. And because we're doing this at one point in time, we don't want to necessarily include the endpoints. So let me give you another example of a completed parabola that maybe opens down. If this is my function, I can hopefully recognize that I have a horizontal tangent. Oops, I'll just make it bigger. Up here, right, my turning point. I will apologize in advance for my drawings. They always leave something to be desired. So if that's the horizontal tangent, that's my turning point, right, that relative max or min that we were talking about with the critical values before, I can say if I look at a point over here to the left of that, all of my slopes of my tangent lines are positive. And if I look to the right of that turning point, all of the slopes of my tangent lines are negative. And if you look at that turning point, your slope is 0. It is neither positive nor negative. So when I write that out in terms of increasing and decreasing, because now we can be talking about one moment in time, I don't want to include, per se, the turning point because my slope is not positive there. My slope is 0. So I don't want to include that. I would just say that it's, for example, negative infinity to whatever that x value is, I am increasing, and then whatever this x value is to positive infinity, I'm decreasing. And so that's how we're going to look at this. And so now if I fill in the rest here, as f prime of x is negative for all x in AB, then we say f is decreasing, which I just showed you on the graph above. And then if f prime of x equals 0, we say f is constant on A to B because it may not just be for one moment in time. Maybe we have a curve that does something like so, and then it stays constant, and then it dips. Okay, so I kind of outlined some tests here for the, or some steps, excuse me, for the first derivative test, but we'll go through these. We are going to find critical values, so this is very important that you practice your critical values from the previous sections. You're going to write these values as intervals. Okay, include the entire domain of the function and make sure you include restrictions to that domain as well. And then we're going to do that as intervals on a number line. I use a number line. And then we're going to pick as easy as we can, right? That's why I say relatively easy values that are in those intervals that we have, and I'll show you what I mean here in a second, and see what the sign of f of x is. F prime of x. Is it positive? Is it negative? What is it? We don't necessarily care about the exact value, we just care about the sign of it. And then we make our conclusion based on that. Are we increasing, are we decreasing, or are we constant? So let's look at one. This one has been completed for you just so you can see what a polynomial would look like, so I can talk about it right now. Find critical numbers first, then find the open intervals on which the function is increasing and decreasing, and locate all relative extrema. So the function that I was given was 2x cubed plus 3x squared minus 12x. So there are no restrictions to the domain, so that might be something that I want to note from the beginning here. This domain is all reals. Same thing is true for the domain of the derivative. It is all reals. So if we remember our critical values discussion, there would be a second part or something that I would also have to look into, or second piece of that definition rather, which is, are there any new restrictions to the domain of my derivative? And if I'm answering no, then I have no other critical values to add to that list. So I have the same domain for the original and the derivative, so I have no new other critical values to look at. So I'm just dealing with my first derivative. And I'm going to set it equal to 0 because that's going to help me find potential, I'm going to say potential, turning points. Okay, just potential turning points. So I factored, and I found two potential values where I turn around. Now again, it's not guaranteeing anything, so I go over to my number line. And it's very important that you label your number line f prime of x because we're going to do a very similar process for f double prime, but my conclusions won't be the same. So my conclusion for f prime is whether my function will be increasing or decreasing, okay? So what I did is I put those values, -2 and +1, in numerical order on my number lines. That's what I started with, -2 and +1. And then if you pick a number in that gray section anywhere, so any number from -infinity to -2, so maybe a -3, a -4, a -5, etc., and put it into f prime, then you will see a positive value. So f prime is positive, which means my function is increasing, and I do usually draw what that means. And then again, if you put in a number between -2 and 1 in that yellow section, maybe a 0, maybe a -1.3, whatever you decide to do, and I let technology help me with calculating those values, then I will see a negative first derivative. And then again in that last section there, if I put in something greater than 1, I will see a positive. Please do not automatically assume that if you start positive, you automatically alternate throughout, because that is not the case at all. And then I do want to make note that in order to find these relative min and relative maxes, that's pretty dark, sorry about that, I want to make sure that you understand these are points on the original curve. So once you get these potential turning points, you are just going to evaluate what is f of 1 and what is f of -2 to determine the actual value of the points. But once you say, okay, f of 1 is -7 and f of -2 is 20, you still don't know which one is your relative max and which one is your relative min. And we talked about that in the previous video. You can't only look at y values unless you're trying to find the absolute max or min, because that's the absolute highest point. We're looking for turning points, so we're talking about behavior of the graph. So that's where I like my arrows here on the number line. I'm increasing to a max and decreasing after. So I can tell that this kind of looks like so, so that should be a maximum. So I'm going to say relative maximum. And remember, if they ask you for a value, you are typing in the y value. Or if they ask you for the whole coordinate pair, then you could type, -2, 20 into the pair. And then you decrease to a min and increase after. And so 1, which would be my -7 here, will be my relative or local minimum. Again, not because of position vertically, but because of my behavior, increasing to a max, decreasing to a min. And so I just wrote all that down. And then I transfer. If I'm trying to find my interval of increase and decrease, I have this number line over here ready to go. So my increasing are the 2 on the ends, -infinity to -2, union with 1 to infinity. I'm reading my number line. And then my decreasing here is everything in between that -2 and 1 in that middle section. And again, you don't want to include, for example, the -2 because as you'll see, -2 is used in both the increasing and decreasing because at x equals -2, you're actually constant. You're neither increasing nor decreasing. Okay, so let's do this from start to finish with another problem. Okay, so here is my second problem. And the first thing that I think it's very, very important for you to note is your domain. This is an algebraic thing that you talked about, obviously, before calculus, but it often gets forgotten. So the domain of my original function, we already know, we've talked about it quite a bit, you cannot divide by 0. So whether you just write x cannot be 0, or whether you write it in interval notation, it's more for you than it is for an answer for the problem. So it doesn't really matter at this point. What's important to note that if x cannot be 0, that is a jump in your function or a jump in your curve. So if you were increasing and you get to 0, I don't care if it's a whole or a vertical asymptote, you really don't know what you're doing on the other side of that. So we have to use that 0 in our number line. Okay. So now I'll go ahead and I will find the first derivative. So y prime equals 1. And then this, if I want to do a rewrite, is 1x to the -1. So this will become -1x to the -2, or y prime equals 1 minus 1 over x squared. Take as long as you need to find that derivative. You can pause this video at any time. Okay, so again, I have the same restriction that I had before. X can still not be 0, so I don't necessarily have a new restriction. It's not going to necessarily add to my critical values list at all if I did have to find those or list those out, because I already knew x could not be 0. Okay, so I'm going to set this equal to 0 and try to find possible turning points. You can multiply through everything by x squared. You can add one fraction to the other side, and now you have a proportion. You will solve this using your algebra that is comfortable to you. So that is 0 times the x squared is 0. 1 times x squared is x squared. And these x squareds will divide to 1. So it just leaves me with the 1. I like to show this factored, but this is entirely up to you. That is a difference of squares, so it factors into its 2 conjugates. And again, go as fast or as slow through that solving as you need. You can pause at any time. Okay, so again, these, I want to make it very clear, are possible turning points or possible relative extrema. Nothing guarantees them to be this way. These are just possible. Okay, so on my number line, you'll see I kind of cheated here. I already have a number line drawn. First and most important thing, oops, this is an F, excuse me, this is Y, so I will label it. This is Y prime. Because again, we're going to be doing something very similar in another follow-up video here with the second derivative, so I want us to be clear about what our conclusions are based on which number line we are doing and we are working with. And we are working with the first derivative, so all of our conclusions will be increasing or decreasing. So you'll notice that I have three numbers here that should go on my number line. And I really only found two possible turning points. That is a reminder that this domain restriction from the beginning needs to be included. So I'm going to write these numbers in numerical order on my number line. So -1 will come first, then 0, and then 1. But I'm going to do something else so I also know why each number is there. So -1 and 1 are those possible turning points that I think might become a relative max or min. But this 0, I'm not expecting it to be a max or min at all. It's a domain restriction. And what kind of domain restriction is it? Well, you have 1 in your numerator. So if x is 0, that would be 1 divided by 0. That's a vertical asymptote. Okay, so I draw it, and again, if you're unsure, you can always draw the original and you will see a vertical asymptote at x equals 0. So I draw that on my number line because again, we're going to use this eventually. We're going to use these number lines to get a really good drawing here on our own without the use of our graphing calculator, and I will show you this one when we're done here. So okay, now I'm going to test each section, and I hope it kind of makes sense to you that I have one section here yellow, one section here in the blue, one section here green, and this section here. Right, that's kind of that purpley pink color. And I'm just going to test a number in each section, and I can do this by hand, or I can do this using my calculator, whatever you find to be easier. So in that first section, if I'm looking left to right, I'll put in a number like -2 or -3, something like so. So y prime would be 1 minus, if I put in a -3, that'd be 1/9. That is for sure positive. So I know my function is increasing. Again, a derivative is a descriptor, or an adjective, if you will, of our original function. So it tells us if your first derivative is positive, that the original function is increasing. But then if I put in something in between, again, don't assume that you just always alternate perfectly. If I put in something in between 0 and -1, now I'm putting in a fraction. So maybe I'm putting in something like -1/2. So that becomes y prime 1 minus 1 over 1/4, or 1 minus 4. That's definitely negative. And again, you could allow your calculator to help you. It's just computation, so it's your comfort level. So because my first derivative is negative, I would say my function is decreasing. And then I go to the other side, and this should make sense to you, or the other side of my vertical asymptote rather, in the green here. It should make a little bit of sense that if I'm putting in a positive 1/2, I get kind of the same result, because whether you square -1/2 or square positive 1/2, you still get a fourth. So I'm still getting 1 minus 4, so it's still going to be negative. So I'm decreasing. And then if I put something in greater than 1, maybe 2, 3, or 4, the same situation will occur at what I started with. I get a positive first derivative, so I would say my function is increasing. Okay, so this is what my number line will look like, and I can certainly write out the intervals of increase and decrease based on that number line. So I increase -∞ to -1, and I'll union that with over here. So I just circled my increase intervals, 1 to infinity. And I decrease, now I am decreasing this whole time in between here from -1 to 1. And if you didn't have that vertical asymptote drawn, it might be really appealing to just say -1 to 1 and not think twice about it. But I have to stop at 0 because it's a domain restriction. So I'm going -1 to 0, and I'll union that with 0 to 1. Again, nothing is included. Okay, so now what they're going to ask you is which of these is a relative max or relative min. So this is the last thing for this problem here. So again, I think that turning point occurs at -1. So I want to evaluate your function, which is y equals x plus 1 over x at x equals -1 and at x equals 1. All right, so if x equals -1, I get -1 plus 1 over -1. -1 plus -1 is -2. So I have a point here, -1, -2. And if I put in a 1, I get y equals 2. So I have the point 1, 2. And if I wasn't careful, I might only be paying attention to these y values, and I might say that my relative max is at 2 and my relative min is at -2. And that's not the case because, again, look at your number line. Okay, so I'm going to make sure that I use this number line up above. And I can see that this turning point at -1 is going to be a relative maximum because you increase to a max and decrease after. So that -1 value, this is my relative max. Okay, so my relative max would be at -2, or if you were writing this, I could say at the point -1 comma -2, because we will get to the point where we need to graph this, so you're going to need to know the x value and the y value. And the relative minimum is because you decrease to a min and increase after. So I would say that's at y equals 2 or the point 1, 2. Okay, so again, you can't just look at the end point unless you're trying to find that absolute max and min. But if you're talking about the calculus of it, that relative or local max and min, you've got to look at the behavior of that original graph. So let's take a look at what this curve looks like. Okay, so if I go to my graphing calculator and I hit y equals, I can type in my original function, x plus 1 over x. And I'm going to shorten up my window just a little bit just because I know these max and mins are only as high as 2 and -2. So I'm going to hit window, and again, I'm just going to, I will say the word zoom, but I'm not going to use my zoom. I'm going to just say x min, maybe we just go -5 to 5. X scale 1 is fine, and y min, I'll do the same because again, I think this graph is going to be pretty small, so this should give me a good view of it. And if I hit graph, I'm going to be able to see exactly what we thought, and I'll just go over a couple key features, then we'll be done with this part of it. So if I look at this graph, I am increasing until an x value of -1, and I can see my relative max turning point is going to be below my relative minimum turning point just by looking at this. So, and this will happen more than once when you have a disjointed graph or a discontinuous function. So I'm increasing to my relative max, so -infinity to -1, which is what we said. And then I'm decreasing from 1 to 0. I can visually see this vertical asymptote or this point of discontinuity on the graph at x equals 0. So then from 0 to 1, I'm decreasing. Again, read the graph left to right, just like you would read your book. And then there's my relative minimum. And then from x equals 1 to infinity, I'm increasing again. And that is exactly what we said for the intervals that we have. There they are. So negative infinity to negative 1, union with 1 to infinity for increasing and decreasing the in-between. I hope you found this helpful.